A bit of motivation for this. So we have a lot of type theories that let us reason nicely about some mathematical structures. So for example, extensional type theory let us reason nicely about sets. Homotopy type theory let us reason nicely about sets. What we would like is some notion of directed type theory that let us reason nicely about categories. So the rough idea right now that we are taking is start with the Martin-Love type theory and the groupoid model. Then we just import the rules within the semantics of the category model back to the syntax. So for example, we can add an op type constructor. We can also add a home type constructor. All of this has been previously done by North and many other people plenty of times. The new contribution here is we add a new context extension operation, which captures dependent two-sided fibrations, which is a notion I'll be introducing in a bit. So to recap, the groupoid model is as follows. So we interpret contexts as groupoids. In particular, the empty context is interpreted as the terminal groupoid. Types in context are interpreted as functors. So a type A in context gamma is interpreted as a functor A from gamma to groupoid. The context extension is the growth in the construction of the functor associated to the type A. And terms in a context are sections of the canonical projection from the growth and deconstructions. So in particular, we can interpret as follows these judgments. So a type in the empty context would be a functor to groupoid from the terminal groupoid, which is the same thing as a groupoid A. And a section or a term FA in context A would be a section from A to A dot B. And when B is constant, this is the same thing as a functor from A to B. So this kind of sketches how this language let us reason nicely about groupoids. So now we want to do the category model. So we look at each time the word groupoid is mentioned, and we write category, and that's it. Except that now the tricky part is the type constructors. There are a lot of many tricky things with them. I want to focus on the home type constructor, which is the analog of the identity type constructor. So let's recap how it looks. I will be working on the empty context just for simplicity, but everything works for non-empty context. So given some type A, if we, the formation rule says that for any A and B, we have a type of identities between these. And the interpretation is the home functor that goes from A dot A to groupoid. And this is indeed a functor because since we're working with groupoids, we can just invert this one and get a path from A prime to B prime. So if we want to do this for categories instead, we again see every instance of the word groupoid or identity and replace it with the word home or cat. Except that this is not working that well because, of course, the home functor is not of this signature. It rather has to consider A op. So this forces us to introduce an op type constructor. So this works well. The more interesting rule is the introduction. So again, the rule in usual Martin-Love type theory is as follows. So given some type A and some A and A, we have a term of REFL in the identities from A to A. The interpretation is a morphism REFL below. So it's a diagonal where a morphism REFL that lives against the diagonal here. And this is just assigning to each A in A this identity morphism between it. And functoriality says that this is square terms. So what has been done previously in other work by North is extend this to the category model, but then this will not work. So what she does is add a core type constructor so that we can make sense of this diagonal here. What we are going to do right now instead is massage a little bit more these interpretations so that it's easier to extend to the category model. So what we're doing now is instead of writing this, note that this object is, or this category in the category model is the same thing as the arrow category. In this projection is the domain and codomain projection. So now that we are with this version of the interpretation, we now replace the words identity by the words home, and now this works as an interpretation for the category mode. But we have to think a little bit of what have we just done. What we have just done is to each perfunctor assign, for each perfunctor A up times A, to cat assign some display category that let us pull back like this. So this notion has already been quite studied, was introduced by Street, and the definition is as follows. So given some category A and some category B, a two-sided fibration from A to B is a category C equipped with the following span P and Q from A to B, that is a diagram like this, such that P is an up fibration and Q is a fibration and some coherences hold. But we are doing dependent type theory, so we would like the dependent version of this. That is when B is dependent on A. Again, it's not clear how to straightly generalize this from this definition, but we can massage this definition a bit. So instead of talking about spans, we talk about a functor Q from C to A times B, because we are particularly interested in the category of categories. Now, the second point says that the projection to A is an up fibration. And the third point we have replaced by saying that for each A in A, the restriction of Q to the fiber over A is a fibration. I massage this like this so that this notion makes sense once we pass to the dependent version. The dependent version is replace P in cat in the functor Q from C to A times B to just be B from A to cat and a functor Q from C to A dot B. Also, the coherences have to be somewhat adapted, but it's somewhat straightforward. So why is this useful? So Rothendick showed that there's an equivalence of categories between fibrations over A and functors from A up to cat. The analog for the two-sided fibrations is that the category of two-sided fibrations from A to B is equivalent to functors from A times B up to cat. The dependent two-sided fibration version is very similar to the previous one, except that now this is equivalent to functors from A dot B and then the opposite involution to cat. So in particular, we are getting some unstraightening operation that lets us make each functor into some displayed category, which is precisely what we use and precisely what we need. So we now come back to the syntax, and in addition to the usual context extension rule, we have a new context extension, which precisely captures this unstraightening. So given some A and some B that depends on A, and some C that depends on B contravariantly, but covariantly on A, we are able to form this new context, which is the dependent two-sided fibration. And so we can do a new home introduction rule. So we can apply this to the home introduction rule. So we know that home depends contravariantly on A and covariantly on B. We have modified this so that it has the right signature. And then we're able to derive the existence of this context, which, if you compute the definitions, is precisely the same thing as the arrow category, just as we wanted. So now we can make sense of the introduction rule. So, right, so maybe a little mention of this 12. So because we are now doing dependent two-sided fibrations and no longer just up fibrations or fibrations, we have to annotate that we are doing something different. And we now also have to do this here for the home introduction rule. This REFL morphism is, again, a diagonal, which is to say a section of a pullback of a dependent two-sided fibration. And sadly, dependent two-sided fibrations are not stable under pullback. So I need to introduce a new judgment that lets me tell the system that this is precisely a diagonal like this. So far, so good. Now, we also get a home elimination rule almost pretty much for free, which looks precisely as one would expect, I guess, except that B should be on the right and A should be on the left, what would normally expect. But omitting that, it's the same thing as the usual elimination rule for the identity type, again, minus the 12. But so that means that dependent two-sided, the path object lives against fibrations. But in fact, it has a slightly stronger property, which says that it lives against a huge class of dependent two-sided fibrations. So that means that when D is also covariant on B, and we pull back the dependent two-sided unstraightening construction and just defining on REFL, then we get one section for all the arrow category. Again, this is very closely related to the groupoid version. In fact, if you look at proofs, they look exactly the same. So what do we get? We get some partial solutions for some problems that we were having with our previous version using the core. So now terms are fully functorial. For example, using the elimination principle, we can show that given some f from A and B, we have some ff from fa to fb. But now the point is that it's functorial both in B and also in A. So the variables are not constrained to be on the core anymore. And probably the main selling point is that the analog of homotopy in HOT, which is a judgment like this, is interpreted as natural transformations F to G in the model, which is something that would not hold if one were to take just the core here. So all these tools and the elimination principle let us prove Yoneda inside this theory. So there is some amount of expressivity here. So in summary, we start from the groupoid model and add categories as types, a home type constructor, an op type constructor. And the main contribution right now is the new context extension, which recovers the arrow category, which let us get this nice elimination principle and introduction rule. So this is all work in progress. So there's a lot of things that I would like to know. And if any of you have any suggestions, I would be very happy to hear them. Also, any comment in general. So I would like to understand if there's a right notion of factorization system for these things. How can we do something about the lack of stability and the pullback? How do they interact with pi types, characterization as a lax normal functor from A to B to prof? There's also the very obvious question of, well, what about n-sided fibrations? And it turns out that this question doesn't even make sense for a decent amount of cases, but some combinations do make sense. And it's very unclear to me which combinations precisely are the ones that do make sense. There's also the fact that we have to use explicit substitutions. And yeah, I would like to write a type checker for this, but I have no idea how to deal with these many different judgments that are all over the place. Thanks.